I think so. Yeah.
Okay, great. Thanks. So hey everyone. So welcome back. So I hope the first homework assignment went well. So you should hope you all realized, or almost all of you realized, it was due today at 5. We'll probably be a little flexible with the deadline for the first assignment, but it's just too much bookkeeping otherwise if after this one. So we'll keep in mind there's a deadline of 5, which is before class. I do that so that you can do it before class, and where you should still have time to get here and make it to class on time and everything like that. Yeah.
Are you going to be releasing solutions?
Probably not solutions, but I'll probably make the TAs will all know the solutions and be able to will be able to kind of tell you what the right answer was. Yeah.
Would you mind at some point just briefly talking about the Las Vegas algorithm?
Sure. Yeah. So I can start by, I'll talk about it. If you ask me again on Monday, the start of class, I'll talk about it. I don't want to talk about solutions because some people are turning them in a little bit late. So just a reminder on the late policy. If you miss the deadline but turn it in within 24 hours, you get 10% off. So you lose 10 points out of this assignment. If you turn in within 48 hours, then you get 20% off. After that, we won't accept late ones anymore. Okay, so there's, if you didn't quite get in or you realize you need to change something, it's only 10% off. You can decide whether that's worth it to change it or not, or to turn in late. Right. So just to say a little bit about the homework without discussing like anything too specific. It's about the solutions. So I hope you kind of got a chance to kind of see how the choice of how you implemented the algorithms affected whether you can scale to these large sizes. I've heard everywhere from just a few seconds to complete all the experiments to spending a long time optimizing in MATLAB or R and it taking like an hour or so to finish them. That some of it has to do with the language you use, and some has to do with the data structures and how you actually do the programming of stuff. Someone else came and mentioned to me an interesting issue. They scaled beyond what I'd asked to scale, and they found that the rate at finding the collisions in the birthday paradox was changing. Right. So they were finding collisions more frequently than before. So why could this happen? Yeah.
Issues with the random number generator thing?
Yeah. So what could go wrong with the random number generator?
It's not uniform.
Yeah. So one is it cannot be uniform. Anything?
If your data structure has to resize and then copy.
So if you're using like a built-in hash table, yeah, and you get an accidental collision.
So like if you're using something like an array list that will extend itself rather than just using an array.
Yeah.
And it has to double in size.
But so let's assume. So this seems like more like a timing issue, right? So this can lead to some timing where you get like a big jump in the timing graph. You cross a barrier, it leads to a data structure resizing, and then you get any time beyond that, you get a big jump. But this,
you're talking about getting collisions, really.
Yeah, the actual finding the collisions. So one of the things that can happen is, often built into programming languages, you have some sort of utility where you can draw some U, which is uniform at random between 0 and 1. right? So often this is what's built into languages. This is supposed to be a random real value between 0 and 1, right? But if you've taken a basic computing class, you know that you can't store a perfect real value in there. It's either stored like as a double, or like a float. These are representations of the number, and they have a limited amount of precision, right? And so you don't even need to think about how you would actually represent these, but what's going into here. When you actually do this, the computer is generating some stream of bits, right? And it's somehow converting these bits into a double or float. And typically what happens is it says, the computer says, I'm going to do a certain number of these bits, right? Maybe it's 8 or it's 16, and then it's converting those in some way into a float or a double or some other representation. But the built-in way says most times people only need precision up to a certain level, so I'll stop generating bits. But real numbers should have an infinite number of bits, right? So this is what's actually going on under the hood, and that's why one of the questions, I forget if it was the third or the fourth one, I asked you, what if you could only generate these zeros or ones, right? If you could only generate these, then how would you generate these random numbers? And so that's what's actually going on, and these randomness is a resource. So I talked to some other people who said they tried different ways of generating these random numbers, and depending on how they did it, it took a lot more time or a lot less time. When you're dealing with randomness, it's important to kind of think about these things because these can end up being the bottlenecks in the process. So, I hope this first homework kind of sets the table for some of the other stuff we'll do, even though it wasn't a very kind of a direct application with data. The next one, which I guess I need to post pretty soon, I'll try and do it by early next week, will be more directly associated with analyzing data. We'll build on some of the kind of basic structures and ideas that we talked about in the first one. Okay. All right, so let's get back. So the topic for today is going to be locality sensitive hashing. And so this is often abbreviated as LSH. Okay. So the problem we want to do, there are two kind of main questions that we want to be able to answer. Okay, so Q1, so the first one is, so the input to something is let's put this above Q1 here. There's going to be a large set of size n and some sort of a distance function or a similarity function. Okay, so this is going to be the input. Okay, and then given this, two very kind of common tasks that you're going to have in either explicitly as the data mining objective or inside of some other operation. So for instance, when we talk about clustering, this will be kind of at the center of anything we talk about is, we'll call this set, P. So, given a query Q, find all P in P close to Q. Okay, so by close, that's somehow related to this distance or this notion of similarity. And so it can mean different things. Either you have some threshold, you say, I want to find all elements of this set which are within some distance, or I want to find all all things that have a similarity that's higher than some value. And sometimes you're told this ahead of time. I just want to say, I know this threshold. I want to find all of them. Maybe other times you just say, I want to find the single closest item, right? The single thing which is closest. So that means the smallest distance or the largest similarity. Other times you say, I want to find the 10% of things which are closest, or the 100 things which are the closest. And so you're instead given a number instead of that. And so these turns out to be kind of sub-questions of different variations of this first question here. Find all the things that are close. And if you don't know the threshold ahead of time, often you kind of try various thresholds and do like a binary search on that threshold to answer some of these other questions. So the other one is given P, find all pairs P1 and P2 both in P that are close. Okay, again, you can say, given the underlying distance, you want the distance between the pairs to be close. You want it to be below a threshold or the similarity above a threshold. Or you can say, if you're trying to find the closest pair, this turns out to be, there's a whole set of different techniques for this. But if you want to find kind of a bunch of things which are all close, then it's kind of is very similar to this sort of problem. Okay, so this so again, so these two problems, it's if you can calculate the distance or the similarity, say efficiently, say in constant time, then there's a pretty straightforward solution to both of these. But this one would take O of n time, and this one would take O of n squared time. So there are n choose two pairs of these points, and you'd have to check the threshold between all of them, right? And this one you'd have to, given a query point, compute the distance to every point, and that's going to take linear time. And if you're doing this over and over again, or your n is very large, and you just want to say, I found, let's say you're searching something on Google, you found a web page, and you said, I want to find all the similar web pages to this. So every time, I think often built into Google or Bing and stuff, they have some sort of built-in thing where you can do this. Now, for them, it's often pre-computed in some way, but they don't want to have to run this query over and over again, and they don't want to have to do this kind of from scratch for all of the web pages they have. They somehow want to be able to do this in less than O of n time. And this, finding all close pairs, right? So find all near duplicates of web pages, because I want to weed those out. Or I want to find these, I'm trying to find spam in comments on someone's blog, so I can automatically block the spam. So a lot of times that's because those comments are ones which are very close to another comment because they're written by a bot. If it just says, great post or something, then you need to say, well, those are all the same, a different category. But if you find other ones which are longer and are almost the same as something else you saw, those are probably spam. You want to be able to identify those and filter them out. But you don't want to have to do this with check all pairs. This is going to be too slow. Okay. Uh-oh. All right. Okay, so let's, so we talked, I mentioned before that if the objects you have, so let's assume that P is going to be is a subset of R. Okay, so R is a set of real numbers, right? So it's it could be integers or whatever. It's not so important, but it's not these high-dimensional vectors. Let's say the simple case here. So it's a subset. That means everything here is these real vectors. So we have something like values 1, 2, 7, 11, 12, 16, 18, 20, 22, right? So let's assume this is our data. And if we can pre-sort this data, like I've written it pre-sorted, I want to find say, the closest, or here, let's do this instead. Find the points in P. So with distance between P and let's say 8 to be less than 2. Okay, less than or equal than 2. So I can so how would I quickly do this? Yeah.
First, find the element that's closest to 8.
Well, so how would you find the element that's closest to 8? Right.
Binary search.
Yeah, right. So I can do a binary search, or I can build. I can implicitly have a binary tree. I search in the middle. I know 8 is less than 12. I go to 7. 7 is smaller than 8, but it's close, right? I go over 1. This is larger than 8, and it's too big. I don't want to count it, and I can check to the left of 7. This is too small, so my only answer is 7, right? And I can do this if this grows to size n. Then this operation takes. If there are k things close, I can do this in log n plus k. So I can do a linear scan once I find one that's close and check all the neighbors. And that takes k time, and log n to find this. Okay, so this is good. Other question, so that was like question 1. If I want to say find all pairs, P, let's say Q, in P such that D, P, Q is less than or equal to 2, then how would I do this efficiently? Yep.
Do a linear search for the whole thing.
Yeah, so what you want to do is you're going to keep 2 pointers, keep this pointer, and then you move this forward, and until this becomes a distance of further than 2 away from 1. And anything in these pairs, with this pointer, you move it as closer here, right? And then you move this pointer over, and then you can see if it's closer then everything left of this pointer where you match with 1 will also be close to 2 because it's closer than them. And so you can do a scan of moving each pointer across once, and you can kind of do this in one scan with these 2 pointers moving across, right? So you can do this in O of n time. So these are much less. The log n plus k and the O of n time, I think you probably need O of n. Yeah, then you can do it in O of, you probably need O of n plus k, where k is the number of close pairs that is reported. But these are much less than linear for this one and n squared for this one, right? So it turns out that this specific approach is going to be hard to generalize to higher dimensions. We'll actually talk about something next week that kind of tries to generalize this. There's a different way of doing this that is kind of not how you'd usually do it in a data structures class. What you kind of want to do instead is draw some kind of bins around these objects. You know, maybe 7 is in its own bin, 11 and 12, 16 and 18, and in these bins, okay? And then you can and there may even be some kind of implicit empty bins in between here. And when you see a value 8, you can kind of directly hash it into one of these bins. Maybe it goes into this bin has 7 in it. And you know that if something is close, it'll either be in this bin and you look at all these things, or one of the bins that's a neighbor. So you just have to check a constant number of bins once you've hashed it into here. Right? And then if you want to find all close pairs, they're either going to lie in the same bin or in bins which are neighboring to each other. So you can then kind of scan across these. Okay, and so, if you think about this carefully, there may be either the bins might be bigger than you'd want, or there are some issues on the boundary of whether things are in the same bin or not. And so it's a little messier to do this. The data structure is not as clean, but it's going to turn out this general approach of these binning is going to be more effective at generalizing to these nonlinear settings. Okay. So in general, what we're going to talk about today is this locality-sensitive hashing, so basically what this does is it defines, again, these class of hash functions, where you draw a hash function out here, and this process is random. And then you're going to have something that happens with some probability based on the choice of this random hash function. Okay, in fact, what you want you have two objects, A and B, which are going to be in some data set that you want to understand. And you want two kind of two criteria here. One is that the probability that the hash of A is equal to the hash of B is going to be greater than some parameter alpha. And so we're going to have these 4 parameters which describe this, and I'll write them down, and then I'll kind of take some time to help you interpret what they mean. So the probability, if it's greater than some parameter alpha, this is true if the distance between A and B is going to be less than gamma. Okay, and then, so you're saying that if the probability so if the distance is small, it's less than some threshold, then the probability that they hash together is similar, is high. It's greater than some alpha. So you can satisfy just this first one by saying, well, let's always have them hash together. So this isn't enough by itself. So you also need the probability that these hash together is going to be less than some beta if the distance is far, is going to be greater than phi. Okay? So if the distance is far, greater than some value phi, then you want the probability they hash together to be small. Okay, so we'll see 2 examples of this in class today. One will be based on the output we got from the min hashing algorithm, and another one will be useful for understanding Euclidean distance. So high dimensional Euclidean distance. And again, this is based on a distance function. You can change this distance. So this parameters are based on similarity. So say if the similarity is high, then this is true. And if the similarity is low, then the probability that they hash together is small. So you can change the similarity in here as well. And so we'll show with the min hashing, we'll actually use that, d of a b is equal to 1 minus the similarity of a b. So you can plug in the similarity in place here with 1 minus, but this is a little bit cleaner. Okay, so in general, so if you have a hash function, a family of hash functions that satisfies above, so if it satisfies 1 and 2, then you say that this is a gamma phi alpha beta sensitive hash family. Okay, and the hash family, the process of generating this hash function, you can think of this as you have some algorithm which generates a hash function, and then it has these properties, and this will be some randomized algorithm. Another way of thinking about it. Okay, so in general, the kind of what you want is that So, so you want that this gap between alpha minus beta, you want this gap to be large. This is good. And you want the gap between phi minus gamma to be small. Right? If these are true, that's good. So it means that if there's some you want that, it's a very high probability that if they hash together, the distance is small, and if the distance is large, there's a low probability that they hash together, right? And the small depends on the gap between these values, right? So you want to understand some distance threshold here, and you say if it's less than gamma, then you want them to almost always hash together. This is with probability alpha. And if it's greater than distance is greater than phi, then you want so this probability to be so you want this to be small. Right? So this happens with probably less than beta. Right? So this is sometimes it'll so basically there's going to be some underlying probability that they hash together based on the distance, right? And so if it's less than here, you want this probability to be high. If it becomes larger distance, then you want the probability under this part of the curve to be small. And so this will be the true distance you want to capture. You want to say this was the threshold that we wanted to kind of estimate before. And we can do that just by hashing them into the same bin, right? So if I went back here, if they ended up in the same, I somehow created bins where close things were in the same bin, then I could just hash my query 8 into a bin and find all the similar things looking in that bin. If I wanted to find all pairs that are close, then they would be in the same bin. I just have to look in the bins. Right? So you somehow want to create these bins in an effective way so that you can just look in the right bins and don't have to even do this binary search kind of nonsense. Right? You can just look at the individual bins. So how do we do this, right? Okay. All right, so this kind of definition makes sense? Well, let me go through an example again with the, I'll first go through the example using the result from min hashing. Okay, so let's copy this over quickly. I wish there was a copy thing I can do in the previous slide. So h of A equals h of B. If this is going to be, let's get this right, this is greater than alpha if D of A and B is going to be less than gamma, and probability hash of A equals hash of B is going to be less than beta if the distance between A and B is greater than phi. Okay, so this is the property we want. Where are we? Okay, so now if we look at this, so at this min hashing property we have, this min hash function. Remember how this worked? We had these documents. We turned them into these sets, which we were comparing, right? And we kind of we did a random order of the set elements, and we'll do this random permutation. Was going to be, let's say, is this sigma, and then we have some hash function which was m sigma of a set, and this was equal to the lowest ordered element, and this was based on this value sigma. All right. Right. So we talked about this through writing as a matrix and then reordering the rows of the matrix and so forth. Okay. So this had the property that the Jacquard similarity between A and B was equal to the probability that H of A equals H of B. And so now H is going to be is equal to this function M, right? So and A or B would be one of the sets that we were hashing here, right? So this H is now this function, and the choice of the random permutation is the randomness in this choice of the hash function. Okay, so what we're going to do is we're going to say we're going to set this equal to alpha and equal to beta. They're going to be the same. We wanted alpha minus beta to be small, and we have it equal to 0. So this is great. So this is a special case where we can set these to be the same thing, right? And so before we have some distance function. Remember we had yeah, so basically we have all the probability, was alpha equal, no, sorry, I need to, the threshold, these are not alpha beta, these are going to be the, yeah, this is going to be equal to 1 minus gamma equals 1 minus phi, right? So we're going to use the similarity instead of the distance, right? So that's where the 1 minus is coming from, but the phi and the gamma are going to be exactly this threshold, right? So if you look at this in terms of this similarity that we want, this is the true Jacquard similarity. We're trying to find things larger than this. Then we're setting, if it's larger, then we want them usually to hash together, and we get this probability. And if we want them to be smaller, then we want this to be small, right? So now you kind of have some underlying function, which looks kind of like this. The probability that they hash together will be larger the more the similarity is, and smaller here. Okay. Right, so we'll set this to our threshold, and then we're going to set, and so let this be a threshold tau, and then we can also set alpha equals to 1 minus tau, and beta equals tau, right? So this is let's see. So the probability that they hash together is going to be exactly the similarity. This should be, again, 1 minus, sorry. Right, so the probability that they hash together is going to be exactly the Jacquard similarity. So we're going to set that to be alpha. And the probability that they don't hash together is 1 minus the Jacquard similarity, which is just tau. So this min hash satisfied this property. Okay, is this confusing? A little? Yeah? No? Yeah? Okay, so here's kind of another big picture of what's going on. Right? You want to say that, so in general, if you want that if the similarity is above some threshold, you want them usually to have the hash values be the same. Right? And if it's below the threshold, you don't want them to be the same, so that you can, so then if we repeat this process, we somehow are going to want to make this curve steeper, right? So I drew it in blue here, but you want to make it so that the probability, so it's close to a step function. So this is the probability in this same bin. So you want that if the similarity is small, the probability in the same bin is going to be almost 0. The probability, if the similarity is high, the probability in the same bin is going to be high, right? This is going to go from 0 to 1 here. Okay, and what you're saying is that if I look at this value exactly at this threshold, right? So in general, I can expand this a little bit. So I don't have to have the threshold right here. I can essentially approximate the Jacquard similarity at these values by moving them by phi or theta. But in this case, I'll look exactly at this threshold, right? If I say, if I go back here, I had these two, the distance I wanted was here, but I'm willing to say if they're really small distance, then I want the probability of clashing to be high. If they're really large, I want the probability of them hashing together to be small. If they're in between, I'm not going to care so much. So I have some wiggle room in terms of the actual distance I used. Okay, but if I go, if I'm here, I'm saying I want to put the threshold exactly at this distance. And I want, if they're above this, the probability to be high. They're below it, the probability to be small. And I'm not going to get that exactly. I'm going to get the probability is going to depend exactly on what the Jacquard similarity is. So I can plot this curve, actually, and I'm going to say if the Jacquard similarity is going to go from 0 to 1, and the probability that they intersect is going to be exactly the Jacquard similarity. So I'm going to get a curve that looks like this. So if the Jacquard similarity is 0, the probability this is the probability that H equals that they collide, right? And so it's going to be a linear line from 0 to 1. And if I set now a threshold here, this is 1 minus tau, right? Then I'm more likely to collide if they're larger and less likely to collide if they're smaller. But I'd like the curve instead to look like this. This is kind of what I want to happen, and that way I can I'm gonna miss out on a lot fewer of these things. So right now I have this red curve, and if I just look at one, they're kind of going to hash together. But if I want to look at more of these hash functions and somehow get a curve that looks like this. Okay, so is this kind of seeing how to work it? And remember, these hash functions allow me to put similar things together in this stranger space and just look at these bins. Okay, yeah, question.
So we have control over which hash function we're using. That's the choice we make to turn the red curve into the blue curve. Is that what
Well, the hash function is this red curve, but we somehow need to combine them together to get the blue curve. And that's what I'll explain next. That's going to be the ultimate goal of what's going on here. But what we're given, we need a red curve that has these blue properties for some alpha, beta, gamma, and phi. And then I can combine, if I have them for, the smaller the gap between alpha and beta, the better. The larger the gap between phi and gamma, the better. But if I can once I have these, I can combine them together to get something that looks like the blue curve. I can somehow amplify them. And it'll be different than how we saw that the bunch of these gave us a better estimate of the Jacquard similarity by taking the average. I'm going to do something else now. If I can't just take the average, that won't give me this binning structure. So I need to somehow use these bins. Okay. Yeah.
Can you repeat her question?
Oh, yeah. Sorry, I forget the question. I answered it, but
you want me to repeat it?
yeah,
So I was just wondering how we were going to get from the red curve to the blue curve. We have control over.
yeah. So the question is, how do you get from the red curve to the blue curve? Or what is your hash function that you're given the blue curve or the red curve? You have the red one, which is not very sharp, and you want to make it sharp in some way by amplifying it. Yeah, and so that's what I'm going to explain next. Okay, and then we'll do it with exactly with this min hash function, and then I'll say how to do it for Euclidean distance. And for those, I won't be able to set it so nicely. I'll have to set phi and gamma. I'll have to separate them a little bit. Okay. Okay. So the idea we need is this process that's called banding. And so the thing is, so there are kind of two versions of this, and I don't know, just because I'm a little weird, I like to think of the first one as being if if the first one is corresponding to Papa Bear, and he's going to be very harsh. Okay, he's going to say, I want to look at more than one hash function, and I'm only going to say things are only similar if they always, that's too many L's, I know, always hash to this same bin, right? So I want to apply multiple hash functions, and think of this, I hashed in, so the idea here is one hash function allows me to kind of put things in a one-dimensional order, and I put them someplace on here, someplace on the real line. If I have two hash functions, instead, I can kind of draw this grid. And two things are only similar. Now, if I have 2 points that fall in the same bin in both of these hash functions, right? So I'm doing two random hashes, and if they fall in the same bin in both of them, then I'm going to say, okay, now these are more similar. This is one way to think of amplifying one hash function, right? What's the problem with just doing this? What happens if I keep adding more and more hash functions? So let's say for everything, there's some probability they're not going to hash together, right? So what's going to happen is eventually with many hash functions, there's going to be no collisions. So the probability of hashing together is just going to keep getting smaller and smaller, right? And even if unless things are exactly the same, they're not going to hash in the same bin, right? So I can't just combine things this way. And then there's also the mama bear, and mama is going to be, you have parents. There's the hard parent and the nice parent. It's not always the dad is the hard one, but the mom is going to be forgiving and say that I'll say they're similar if any pair of these hash functions, if any pair collide. Right? So if any pair of them collide, I'll say they're similar. So what's the problem with this situation?
Just the opposite. The more, when you eventually have a ton of them, you'll always get inclusion.
Yeah, so unless things are completely different, or maybe in some cases, even if they are kind of similarity of 0, unless they have similarity of 0 with the min hash, they're never going to hash to the same thing. So so eventually, almost any pair will collide. Okay, so eventually everything is going to collide, and you're not going to be able to tell these apart. Okay, so neither of these is going to work, but there's some combination which is going to work, and this is going to be the baby bear. Right, so the baby bear gets something, doesn't like the porridge too hot or too cold, likes it somewhere in the middle, inherits something from both of the parents here. So what baby bear is going to like this technique that's, baby bear is going to like this, is going to like this technique called banding. Okay, and so the way you're going to think about this is you're going to have a table of all these hash functions. Okay, you're going to have h1, h2, up to hk. And what you're going to say is I'm going to group them together so that I'm going to have a set of b hash functions here. And so then each of these is going to have b of the hash functions. And then the total function, I guess I said, is k. And then you're going to have each of these things is going to be called this is a band. And so then you're going to have R equals K over B of these bands. Okay, so you're going to group them together. And so you're going to do the technique of Papa Bear inside of each of these bands. And then you're going to have Mama Bear across the bands. Okay. Right, so what's going to happen is that if, what you want to say is that they're similar. So they're going to be similar if all H if all the hashes collide in at least one of the bands. So if at least one of these bands have all of them collide. Okay, so what I've done is I've turned one hash function into a set of, I've repeated it k times, and I've turned that into these R more complicated hash functions. Each of the hash functions, they're basically you're going to get something that looks like this. So this is going to be instead of two-dimensional, this is going to be b-dimensional, and you're going to have times r of these. You're going to have r functions which are now more complex. What's going to happen is the larger the dimension b you're going to make, the probability of collision is going to decrease, but then you're going to do that r times, and that's going to allow you to increase the probability again, back to the probability that you wanted. And that probability will correspond with whatever threshold you want to find the similarity, right? So you're going to have the total number, k, of hash functions. You're going to need, and this will be, you're going to need is going to be b times r in order to get, so you'll have k at your disposal, and you need to kind of split them up between the number you go within any one band and the total number of bands that you have. Okay, so is this kind of, at least what we're doing, does this kind of make sense? So the other reason why you can do this is that each of these bands, which was, represented by this, this was the strategy of the Papa Bear, right? Each of these you can treat as a single kind of hash function data structure. What you can do is you can throw the points together, and then you can look at essentially coordinates. Think of it as b different coordinates, and you can turn those into, use those to hash to a single cell into some hash function data structure. It doesn't need to be stored as a b-dimensional array. You can just say, if something lands here, use those b parameters to give me a key to a hash function. And then you can look it up. And then if two things fall to the same thing in your random hash function, which you use to store this in your hash table, right? Then you know they collide. This you can do really fast. You can keep track of these collisions without building out this actual table, because this table may be mainly empty. But if things are similar, they'll fall to the same cell, and so you can store this as one hash table, right? So this you can store. So you can store as a hash table. So you can use this structure very quickly, and then you have R of these hash tables. So every time you use B of the hash functions to generate a B-dimensional key, which you then can convert into a one-dimensional index into a hash table, and then you can see if things collide. And then you check R, you do this R different times to see if there are collisions. And this gives you a data structure to do this quickly, right? Okay, so let's maybe we can come back and I'll answer questions a bit later about the data structure. But let's first see kind of why you get this this similarity curve to kind of become sharper. You go from the straight line to a sharp line, right? So let's explain why this phenomena is working, where this is the similarity and this is the probability of collision. You went from this straight line to something that looks like, this is the probability, something that looks like this. So I want to go through here, and I'll be able to do this with this banding technique. By combine them together in this way, I can go from this kind of flat one to this sharp one. And so that means by using this set of R hash tables, I can quickly check whether things are similar or not, based on some threshold. Okay, so the way to see this is, let's just kind of work through the probability of the collision, and then I'll kind of show you a plot of what this probability looks like, right? Okay, so so remember, we're going to have R bands, and we're going to have B hashes in one band. So I'll just write this up here for reference. Okay. So now, first thing is, so if S is the similarity that we're considering, so we want S times R. So how would so this I can just say as the probability of what? I think I have.
Doesn't that mean the
Okay, no,
in all bands?
I've got, my notes have a mistake. Okay, so S times B, S to the power B.
Colliding in one band.
Yeah, so this is the probability of colliding in one band. So if I have two objects that have a similarity S, remember it's between 0 and 1, then S to the B is the probability they collide in all bands, because I need this event that happens with probability S, and they're all independent, so I can take the product of these probabilities. I get S to the B. Right? And now if I write 1 minus S to the B, this is going to be the probability of not colliding. This is in all hashes. Not colliding in all hash in one band. Right, so this is probably of not finding a collision in the band. Okay, and then I can do 1 minus S to the B to the power R. And so, so if I do this, then this is going to be the probability. If I look over R different bands, this is probably of not colliding in any one band. This is probably of not colliding in all R bands, where I say I collide in a band only if I hit all the hash functions. And then finally, you can get 1 minus S to the B to the power R. And so this is the probability of colliding in any one, or in at least one band. Right? So this kind of makes sense. So let's look at what this function looks like, and I'm going to tell you it's going to kind of look like this S shape here that we want with the steep threshold. Okay, so all right, let's hope this works. So all right. Okay, 1 minus. Let's see, x. So x is going to represent the x-axis, and that's going to represent the similarity. This will be the number of things inside of a band. Let's say this is 3. And we're going to raise this to the power. So let's say there are now 5. So there are going to be 5. There are 5 different bands, and there are 3 things within inside of each band. Okay, so this was the equation I just had that I worked out. And let's view frame limits. Right, so it looks like this. Right, so I'm going from, so if I just drew, so if I did another equation here, so the original one looked like this. It was just a straight line from 0 to 1. This is what I got from just using one of these min-hash functions. And by using 5 bands of size 3, I get this similarity function instead. Okay? So what happens if I change these parameters? I'll leave this one in place. Let me create a new one of these equations. Okay, so let's say I change these parameters. What happens if I change this 5 up to something larger, like a 15? How do you think this curve's going to move? Right, so this was the number of bands. So that means I'm going to have a higher acceptance ratio, the more influence from the mama bear. So it shifts the similarity. It's shifting it to the left. That means something with the smaller similarity is likely to hash together. Okay, a smaller similarity is likely to hash together. And then what happens if I increase this 3? This is something, let's say I increase this to 10. It's going to move it back the other way. Right, moved it back over here. Okay, so let's, so I have some control. I can change these. I can move them back and forth in various ways. Let's try changing this. Let's play with this a little bit. Right, so you can see I can kind of play with it as I move this. I'm sliding it back and forth. And so if I'm around here, I'm about hitting the same kind of threshold. And notice that compared to, just so you can compare them, let's say I have to do 4.5. You can't actually do fractions, but I want them to all go through the same point here. And you can see that this one is using more hash functions, but it's steeper. Right? The more hash functions I use, the steeper I can get this. Right? So if I change this up to, let's say I did this 10, and I made this 30. I need to make this bigger. So, okay, I need to go a lot bigger. All right, so if I do a lot like this, I do 1,000 of these bands, and 900 of these bands and 10 within each band, I get a really steep function here, right? It's getting steeper and steeper. And so, it's not just that I care right about this threshold. So, one of the things that I hope you got away from the lecture where we talked about creating these sets is that there was a lot of choice in how we decided to create these sets, how we did the n-gramming. Did we use stop words? Did we use capitalization or not? Did we use like 2 grams or 3 grams? So this distance is kind of like an object that you shouldn't, or similar as an object you shouldn't trust too much, right? So if I wanted a threshold at 0.5, so if it was greater than 0.5, I wanted to find it, well then, if it was, so I'm looking at the probability that happens right at this threshold in order for it to kind of try and figure out what's going on here. But if I expand it a little bit, say I want a threshold of, say, 0.55, because I didn't trust that distance so much, the probability of it being included jumps up a lot, right? And if something is included that shouldn't have been, it was lower than 0.5, it probably means that the similarity was still pretty high. It was still pretty close to this threshold I wanted. right? So, I'm telling you the bound's right at a threshold, but if I relax it a little bit, it only gets better. And most of the error is going to be stuff right on the boundary, right? So the number of if you work out the math and say, well, how many of these hash functions do I need to get a certain bound? And that'll be these kind of right at a threshold. Well, that's going to give you something that's really pessimistic because the mistakes you're going to tend to make are going to be really close to the boundary. All right, so does everyone kind of, you're going to transform just this linear function by using a bunch of these bands into a much steeper function, and then you can recover things that are really close. Is this kind of making sense? Yeah.
I have a question on the bands. How do we determine these bands of hash functions? And to me, it seems like it's a recursive problem because we need functionally similar hash functions in the same band while bands being distinct from each other. So it's essentially what we're trying to do with the document, except that with hash functions, we're trying to make it functionally similar to.
Yes.
Are we going to predetermine these and fix them static, or are these going to be adaptive and change dynamically?
Right. So the question is, how are we supposed to get all these bands, right? Each of the hash functions, each band took B of the hash functions, right? Where did all these come from? Okay, so if you look back to the min hash, we said in order to approximate the Jacquard similarity, the expected value, to get that to be close, we needed some number of these hash functions. And we can create each of those. Each time we do that, we're doing a random reordering, and you can do multiple random reorderings, right? Or what we did is we have this, we didn't actually need to do a random reordering. We assigned every value using a hash function a random number and kept the smallest random number. Each time we did that, we got a different hash function. So, what I showed before in the last lecture on Monday was how to approximate the Jacquard similarity just using this one long vector. But you can do more with it. You can actually create, you can use those same random numbers that we got from that min hash to build this, to do this banding, to do this locality-sensitive hashing, where we can actually recover all the similar things. So we're going to reuse the hash functions we talked about on Monday.
So those hash functions will group themselves into a single band?
So, what you're going to do is you're going to have a budget of these k hash functions, and you need to put some into each band, and then you want many bands, and you want some in each band. Now, maybe the question is,
How do you know which one falls into a different band?
right. So it's kind of arbitrarily, but what's going on here is, the input is you're going to have a budget of k of these hash functions. Okay, and you need to split. So so you're going to have b in each band and r of these bands, and you know that k equals b times r. So how you split, once you know the values of b and r, you can split them up arbitrarily. It doesn't matter. But the question is, given k, how do you choose the right values of b and r? Right? If you choose b, then r is equal to k divided by b. Right? So if I set, given b, then I can say that r is equal to k divided by b. Right? But how do I make this choice? Right?
Also, if we arbitrarily assign them into random bands, then what if let's say we fix the size of the band size to be 2.
Yeah.
Okay. Let's say what if two points get paid, or two documents get paid in one from each band, but they still be the budget, but they're just across 2 bands.
Yeah. So
I
think I kind of understand your confusion, and I don't quite understand the question, but how would I say something and see if this clears it up? So, each of these hash functions is drawn IID from this family, right? So each of these hash functions are drawn from the family of hash functions, IID. So they're all independent and identical. So there's some probability that I'm going to do something wrong, that I'm going to hash two things, two objects which are very different from each other. For every hash function, the band, they're going to have the same value. That could happen, right? But we, in the previous slide, we bounded what that probability was. It was written by this. So this is the probability that they hash together based on whatever the similarity was. And if the similarity is small, then what's going to happen is we're going to get, it's going to be small is going to be over in this part here. And so it's going to be in this regime. And this curve, this steep curve, is going to represent the probability that they collide in any one band. And that's very close to 0 here. We can drive this down by making these numbers large. Now, this was like 900, so this is probably kind of much larger than you may actually have at your disposal, because you need 10 times 900 actual hash functions to make this happen, right? But it's going to be fairly steep, and if the similarity, if your threshold is 0.5 and your similarity is 0.1, then it's still going to be, this is still going to be pretty close to 0. Even with this one, where I only use 15 bands, at 10% similarity, it's still almost 0 over here. So it could happen, right? It's a randomized algorithm. It could happen, but we can bound this probability and make it small. All right. Good. All right. So let's go back and say, so how do we choose the values of S and R? So kind of the basic idea is to so we want to choose S and R. So this function 1 minus 1 minus S to the B to the R is steepest at this threshold tau. This is the threshold. We want to find similar things that have similarity above this threshold, and we want to not find them if they're below this threshold. So we want to go and look at this curve and slide it back and forth so that the steepest part is going to be right at the threshold we want. And we can do that by adjusting R and B. Okay. And so I'm not going to go through how to do that. You can do it by taking the derivative, and I think you need to find where the first or second derivative is 0, and you can solve for it. But there's kind of a cheat of so the steepest slope turns out to be you want tau to be about 1 over b to the power. I hope I don't. So I'm going off my notes. I may be switching up 1 over b and r here. I did in my notes at some point, but I'll correct them tonight. But this tau should be roughly 1 over b to the power 1 over r. This will get you, the steepest slope will be about tau. And so this means if usually, this tells you if you choose this b and r, where is the threshold? You're finding often you have a threshold and you want to recover b and r from this. And so you can set r equals usually the negative log base s of k. So k is the number you have at your disposal. You set, this should be tau. So you do log base tau, and so, if you're not familiar with logs, this is negative log of k over negative log of tau, right? So if you set r equals to this, and then you can set b, and then b is going to be equal to k divided by r. Okay, and so if you do this, it'll work pretty well. So this is how, given a budget k and a threshold that you want for the similarity, then you can choose r and b in this way. Once you have this, there are kind of two things you can do, right? So once you find things that hash to the same hash function value in every band, in every hash function in at least one of the bands, once you've identified these, either you can just say, okay, these are all the similar things, and just stop there. And this is often what people do. It's often close enough. But if you want to be sure you don't return any false positives, things that are similar, even that you say are similar, even though they aren't beyond your threshold, you can then calculate the similarity of these objects and discard them if the similarity is actually too small. Now, so you can do either. You can either just trust this function. You can work out the probability of actually finding kind of bad things at any threshold based on your similarity, or you can kind of double check the ones you find. You still may miss some things that are similar, but you can make that probability small.
Are the notes correct for the definition of R?
I just saw during the lecture I mixed them up in some location, so I may have R and S mixed up here. I will double check this and I will correct the notes this evening. Yeah. So the B and R may be mixed up. So, but there's some equation here that you can use, and I will make sure this evening that's correct in the notes. Okay, so we're okay. So that's basically how the locality-sensitive hashing works. I was hoping that we have about 10 minutes left, maybe a little less than 10 minutes, and so I'm going to try and tell you how you would do a locality-sensitive hash function for doing Euclidean distance instead. So we talked about the similarity, which is kind of like a Hamming type distance, which is if you want to do the Euclidean distance instead, we can do that. Or if there are any questions on the data structure, how this worked, I'd rather spend time on that than do the Euclidean distance. Okay, great. So you can ask me later if questions arise when you're trying to do this. Okay, so remember the Euclidean distance between A and B. So now both A and B are going to be these vectors in some d-dimensional space. And so often this is written as A minus B, just as the norm of this vector, of subtracting them. And we'll talk more about different distances and notations next week. But this ends up being the square root of I equals 1 to D of, if you look at the coordinates, the ith coordinate of AI minus ith coordinate of BI squared. And so it didn't matter whether you did BI minus AI or AI minus BI because you're squaring it anyways. Okay, so this is the Euclidean distance. And so how do we create these? We're going to create these random bins where similar things wind up in the same bins. So how would we do this? So we have these points, and let's just say that you have A and B are here, and you have some kind of axes here. And so I'll draw in 2D, but think this being much higher. How would we create kind of some random bins, a random hash function? What's kind of a thought of how to do this?
What's the question?
What?
What's the question?
I want to create a hash function, a locality-sensitive hash function that satisfied these properties we wanted. Okay, so what we'll do is we're going to choose a random vector, u, and then this kind of essentially gets, you can kind of think of extending this, and we're going to project A and B onto this one-dimensional subspace. So even if they're in high dimension, you can project them onto this one-dimensional vector. Okay, and then what we're going to do is we're going to I'll still use yellow. Can you see yellow? No? All right. There are only like 3 usable colors on here. So then, then you're going to kind of randomly draw these bin boundaries along here. And say if they fall into the same bin along this one-dimensional line, then they're going to hash the same spot. In fact, probably what you can do is you can do something like, so you're going to project them onto this line. They're going to give you a single value, and then you're going to do mod. You're going to kind of create some bin, and then the bin that's up here is going to be the same bin down here. And you can kind of make some tricks so this actually works. So the hash function is finite. Otherwise, these numbers become, you can have an infinite number of bins, and that might be tricky. But you can actually make this finite. It's a little easier to work with. Okay, so this is kind of pictorially what we're doing. Right? We're taking these high-dimensional points, we're projecting them onto a one-dimensional line, and then we do this bin. Right? So how do you actually do this projection? Does anyone know from, like, how would you calculate this value? I want to say, now this projection ends up being the distance from the origin to the projected point. I want to turn this into a one-dimensional value.
Well, the point, it can be thought of as just a vector from 0 to the origin, so you can just take the dot product.
Yeah, that's right. So a projection onto U is equal to is the dot product. So for a vector A and a unit vector U, or it doesn't even need to be unit vector, it just scales it, then this actually gives me a single value in this one-dimensional line. So this actually gives me the distance from the origin to this point. That's what the dot product is doing. So you probably have seen the dot product before. The dot product is going to be the sum over I equals 1 to D of the ith coordinate of A times the ith coordinate of U. Right? And you just sum these up. That's all the dot product is. And this magically gives you this value, which is a projection. Okay, and so now I want to send this into a bin. Right? So sending this into a bin so what I can do is I can say something like so if I want if I want the bins to be, I need to choose. So you can kind of choose a kind of a threshold for similarity by putting a distance here on this bin. So let's make this a big delta. So what I can do is I can multiply this value A dot U. So this is a scalar times the scalar delta, and then I can take the ceiling of this, or the floor, and then this gives me an integer, right? So now it tells me an integer. These would both fall into a value of 3. So both A and B map into the bin number 3. This is bin number 2. This is bin number 1, 4, 5. And if I want to map this one down to this one, so I have a finite number of bins, then I can do mod, say, like T, if I want to only have T things. And sometimes this is easier to use. So I can do this mod T, and I get it into one of T spots. And this gives me a hash function. So this is going to be H of A. And so the randomness here is going to be in the value U I've picked. So the randomness is in this unit vector U I've chosen. Okay, so we've run out of time. So as a question, just to leave you with, and I'll start next lecture with this. How do you generate a random unit vector? Right? So how do you do that? We talked about often, in the homework you said random bits, how do you get to a random number? We're going to start, we're going to have some value r we're going to get, which is uniform random between 0 and 1. We're going to assume that this is a real number from there, but we're going to do this to get a random unit vector, which is in RD. How do we do this from a random number? We're going to actually need a few of these. Generate a few of these and get to a random unit vector. How would you do this? So think about that, and we'll explain that on Monday and talk about more distances. If you have questions about the project, shoot me email. Otherwise, project proposals are due through Canvas on Monday as well.
So when you were talking about the hash functions basically having an S shape,
Yeah.
that's the sigmoidal shape.
So it looks like a sigmoid. Yeah.
There are about 15, 20 very traditionally commonly used sigmoidal functions. I guess like in math bio, I've seen this particular function.
Yeah. Do we have these slides?
No,